Right, we've made it to the last question of the 2016 AS Physics Unit 1 paper. This is the momentum and Newton's laws question. So a couple of bookwork questions in here for 1 mark. Momentum is a vector. What's meant by a vector? It has size, which we call magnitude, and direction, which a scalar doesn't. And then we have a momentum versus time graph, right? Now this is unusual, I haven't seen many of these. We have two colliding railway wagons, A and B. The collision takes place between point 3 and point 5, so that's the point of collision there shown. And then this is the important bit, they coalesce, they remain joined together after impact. Right. Explain with suitable calculations how the graphs show that external forces on the system are negligible. Right. So don't forget, if there is, if momentum is conserved, I should restart that. The principle of conservation of momentum states that total momentum before equals total momentum after, providing there are no external forces. So let's have a look. The total momentum before is 30 times 10 to the 3 kilograms per meter per second for wagon A and 15 for wagon B. So if I add them up, 30 plus 15 is 45, right? Now the total momentum after the collision, wagon A has gone down to 27, wagon B has come up to 18, 27 plus 18 is also 45, okay? So momentum has been conserved, therefore with no change in momentum there are no external forces. So that was a cheeky way of asking, do you know the law of conservation of momentum? Okay, on to the very last page then. Calculate the final velocity of the two wagons, given that the total mass of the two wagons is 25,000, right? So, we've just shown and worked out previously that the total momentum before and the total momentum after is 45 times 10 to the 3 kilogram meters per second, right? So we know that's the total momentum before. The total momentum after is the total mass multiplied by this new velocity of the two coalesced wagons. They tell us the total mass is 25,000. So if I bring that over as a divide, it'll give me the velocity of the two wagons joined together. It comes out as 1.8 meters per second. State Newton's second law in terms of momentum. So most of you would think Newton's second law, F equals ma. But don't forget, A is V minus U over T. So that's mv minus mu over T. That's final momentum, take away initial momentum, divided by time. Okay, and in words we say the resultant force is the rate of change of momentum, or the difference in momentum over time. Determine from the graph the resultant force on wagon A during the collision. Okay, and it specifically says from the graph. So let's have a look. Here's the graph. Now the time of collision happens between 0.5 and 0.3 seconds. So the duration of that collision is 0.2 seconds. The change in momentum, well, it ended up with a momentum of 18. It started with a momentum of 30. So that change in momentum is 12. I've put the minus there to show that it's a decrease in momentum. The wagon has slowed down. Its mass hasn't changed. Its velocity has. Therefore, it's a negative momentum of minus 12. Now, this question is directly related to your answer to this, right? The resultant force in terms of momentum is the rate of change of momentum, the change in momentum divided by time. The change in momentum is minus 12 times 10 to the 3 kilogram meters per second, and the time it took was 0.2 seconds. So I divide those to get a resultant force of 60,000 newtons, and the minus sign indicates, of course, it is a resistive force acting against the motion. Last question then. So they've talked about Newton's 2, now we're going to talk about Newton's 3. The force experienced by wagon B during the collision is equal and opposite. Straight away you think in Newton's third. State which law of motion this is and explain how the graph confirms it, right? So obviously for 1 mark it's Newton's third law. How does that graph confirm that the force experienced by wagon B is equal and opposite to the force experienced by wagon A. Now, unfortunately, they don't give you any marks for saying things like it's symmetrical about the point of collision. You have to say it confirms a change in momentum and the time of collision are both the same. That's what they were looking for there, right? So it's pretty much you can learn that off by heart out of your notes. Okay, so that's a 2016 paper. I will get the next one up ready over the next couple of days. Peace out, goodbye.